All right, let's get started. Thank you so much for joining today's webinar titled On Device Intelligence Redefining AI LLMs for Healthcare Applications. I am Sagar Makhija, Technical Lead Software Engineer at TCOS, and I will be guiding you through today's session. Before we dive in, let's take a quick look at today's agenda. Here is a quick overview of what we will cover today. We will start by understanding why local AI and LLMs matters, especially in the healthcare and medical devices, what benefits they are bringing compared to cloud-based hosted models. Then I will walk through a short live demo showing on how an on-device LLM really works, from model loading to real-world use cases like OCR data extraction and anomaly detection. Finally, we will wrap up with some of the performance insights and metrics, including memory usage, latency, and model comparison, to see how feasible is local AI. Whatever the AI services we are using from ChatGPT, Gemini, Cloudy are all cloud based, meaning all the data and processing happening on their servers and not on the ours. Every user query or medical data sample must be sent over the internet to those remote servers. That raises the data privacy, compliances, and latency concerns, especially in healthcare. We bring the AI engine itself onto our own hardware. It could be a medical tablet, an Android device, or even a local hosted server with dedicated GPU. By this, models run fully offline, process requests locally, and returns response instantly. No internet dependency, no data leakage. This gives us a full control, total privacy, and independence from third party AI providers, while still enjoying the same intelligence and capabilities. When we say local hosting, it doesn't mean the AI is tied up to one specific device. It simply means the AI models runs within our own controlled environment, not on the external servers. This could be a on device like Android tablet, Windows PC, Linux workstation, or even a Mac machine, where the intelligence is fully embedded. Or it could be hosted on the local servers or workstation and then shared securely with multiple devices over private network, enterprise network, or even a local network. In short, local hosting means the AI still stays within our ecosystem, gives us a flexibility in development, whether it's running on a single device or serving an entire network, while keeping full control over data and access. AI is rapidly transforming every industry from finance and retail to automotive, and healthcare is no exception. In fact, AI potential impact here is even greater because medical systems deal with massive data, complex decision, and strict safety standards. For medical software, AI can automate data extraction, detect anomaly in vital signs, assist clinicals in diagnosis, and even personalize device behavior for each patient. By integrating AI locally directly onto medical device or app, we can make these systems faster, smarter, and more secure, all while protecting sensitive healthcare data. So, it's just not about adding AI, it's about bringing intelligence closer to where decisions are made, right inside the hospital or device itself. Let's take a quick look to poll to understand your perspective. Let me bring the poll on your screen, guys. Poll should be visible on your screen. Question for this poll is: where do you think AI will have the biggest impact in healthcare in next 3 to 5 years? I can see interesting comments, selections of answers. Good to see the variations. Yep, poll has been ended, guys. Thank you so much for participating in poll. That's interesting. We can already see how perspective vary depending on everyone's experience. And as we have seen today, On-device AI is becoming a major enabler that connects all these areas together. Demo. Let's start with the Android side demo. I have prepared two demos based on Android code base built with Kotlin and C++. The first one is patient data extraction from OCR. The second one is anomaly detection based on hardware sensor data. Let's get started one by one. Today, we are going to see a quick demo of AI Engine app, which is built in using Kotlin for Android. This app runs a Llama CPP module integrated through GNI layer, allowing it to execute large language model directly on device without any cloud dependencies. Inside the app, we have included a few pre-trained data like Gamma 2, Gamma 3, 1 billion, Gamma 3, 4 billion. Both have GGUFF format, which is the native format supported by Llama CPP module. We can choose among these models depending on the performance and accuracy required. For this demo, we will select one of the model and run it. So right now I have an actual physical device with me. You can see the device I have. Let me try to mirror this device on your screen. Be patient with me. I hope this device is visible to you. Let me do the bigger screen. Let's expand screen. Yes, it's visible. Okay. Now we have AI app engine already installed on this device. Let me open it. Yep. As I said, we already have some of the pre-trained model inside this device. I'm going to select one of it. It's loading into the memory. Let's wait for it. Yep. We got a success message. The prompt is already defined inside the one of the button. So I have a one button, extract patient info. I have already defined the prompt inside the Android Studio project. It contains the input data, the context, what we need, and the logic to feed it into the model. Let's see, go back to the screen and let's see what is the prompt. So it starts with the context followed by the data, what we have, which is extracted from the OCR. Going back to the Android screen, let's click this button, extract patient info. On click of it, the prompt is now passed down to the model, and this Llama CPP module is being processing the query with the selected model. Let's wait for the response. We are getting the response from model in live. Yep, we are receiving information. As we can see, the output generated is quite close to expected result and in many cases matches the real world data very well. Now, note that the input data we are using here has a lot of garbage and noisy values since it was extracted from A4 page captured using 5 megapixel camera followed by OCR processing. Despite that, the AI model is still able to understand and clearly intercept much of it, which shows the robustness of this device on device interface pipeline. This demo highlights how the AI app engine enables on device intelligence, powerful AI interface running completely offline directly on Android device. Let's go back to the screens. Moving to the next demo, I have already created another prompt inside the Android Studio project similar to the previous one. It includes the same three key parameters, data, goal, and the trigger. Let's check the prompt again. As you can see on the screen, I have written a prompt in three different sections. It starts with the context, followed by the data. And in this case, I also written the prompt to provide a specific format of response. So let's go back to the Android screen. I'm going to restart the application. Yep, application started. Let's load the model again. It provides success message, which is very good. Now, I already defined this prompt inside the anomaly detection button. So when I click this anomaly detect button, this will prompt, this will process the prompt inside the same module. Let's click it. The prompt is being processed now. Bear with me, guys. As we can see, we are getting output from it. It starts with the analysis, is evaluating the actual data, and we are receiving now the response in JSON format. As we can see, the JSON format is matches with the requested format. It has anomaly detected status with yes. It also has anomalies type. It says elevated body temperature and heart rate, followed by the third remedy. As we can see, the output here is very close to the reality and aligned with the expected result. In this case, the input data isn't textual or document based, it's real time data from multiple hardware sensors, including heart rate, SpO2 level, body temperature, user activity patterns such as walking, sitting, or watching TV, environmental data like room temperature, humidity, and even climate conditions like such as rain. Based on this sensor data, the AI models run anomaly detections, help to identify if anything looks unusual, for example, sudden spikes in heart rate or abnormal temperature patterns. What even more interesting is that the model doesn't stop there. It also suggests basic home remedies or first level of recommendation, helping user to take immediate action before consulting a real doctor. This showcases how on-device AI can combine contextual understanding with real-world sensor data to provide personalized healthcare insights, all while running locally on Android device, completely offline. As we saw in the demo, these models are directly tied up to your device RAM capacity. The larger the model, the more memory it consumes. So, if your device has limited RAM, selecting a smaller model become a vital choice for performance and stability. When a model is loaded, it occupies RAM. When it starts processing the request, it needs a significant computational power from either CPU or GPU. Now, GPUs are generally better for AI workloads because they are designed for parallel processing, meaning they can handle thousands of small operations simultaneously. In contrast, CPUs are optimized for sequential tasks, handling fewer operations at once. This makes GPU much faster for running neural networks, matrix calculations, and other AI interface tasks, especially in real time. So, for devices without strong GPUs and or with limited 4 GB or 6 GB of RAM, smaller models are key to keeping the experience smooth. As I mentioned in the previous slide, the model's performance is directly linked to your device RAM capacity. Choosing smaller models are key to keeping the experience smooth and responsive. Beyond that, there are few quick performance tuning tips to get the most out of limited hardware. Tune the workload thread, prefer smaller context window, cap the background services, use the caches wisely. Together, these optimization help maintaining stable, real-time AI responses even in mid-range devices. Let's talk about the architecture. In this architecture, our Android app acts as a primary interface built with the Kotlin-based UI layer where user can interact seamlessly. As we saw in the demo, the app communicates with the GNI layer, which bridges the UI and the Llama CPP module running natively on the device. Here, how the workflow works. The user selects AI model from internal storage through the UI. This selection is passed down the Llama CPP engine via the GNI layer, and then when user selects or send user or query prompt, Llama processes locally using the loaded model and generates the responses in real time. This design combines the flexibility of Android UI with the performance of native C++ interfaces, enabling on-device AI without needing a cloud connection while keeping all the data secure and local. This slide highlights how integration works both on device and on the server using the unified approach for seamless communication. On the Android side, we use AIDL contract that define core functionalities like submit prompt, stream responses, get model listing. On the server side, whether it's running Olama on Windows machine or any other setup, we expose the REST APIs interfaces so that any client, including mobile apps or Postmans, can consume it. Now, moving on the third and the final demo. This is the setup. I'm using a Windows machine with the powerful hardware configuration. Right now, I have a machine with the Ryzen 9 5900XT processor, which is 16 core 32 threads processor, along with a NVIDIA RTX 5060 Ti with the 16 GB of VRAM GPU and also tied up with the 32 GB of system RAM. Last but not least, have a SSD storage for faster operations. Let me bring the system screen in front of you so you can see the performance. I hope this Windows machine is visible to you. Let's open it. On this system, I have installed the Olama, which allow us to run larger AI model efficiently on local hardware. Let's open the CMD and see the services. Olama list list. Yep, we got the notification that Olama service is running in the background. Along with, we got some of the list of models which are already present inside the machine. Now, we are going to use this Olama service with the secondary machine with the help of Postman. Now, we need a local IP address so that Postman can reach to this machine. Let's see what is the IP address. IP config. So IP address is ends with 0.24. Now, let me open the task manager along with it so that we can see some of the more informations. CPU, lots of cores and threads. Right now, nothing is consuming much of it. For GPU, we have 16 GB of VRAM. Along with this, performance is still on near to zero. Just note down the VRAM inside the GPU is barely used. Now, go back to the Postman. Let me bring the Postman on your screen, guys. There's the Postman. It's opening. It's loading. Yep. As you can see, guys, on the Postman, we have the IP address of this machine, which is 0.24. That's correct, and followed by the API. Now, next, inside the post call and under the body, we are saying that we are going to use a gamma 7 billion parameter model, which is already present inside the same machine, and followed by the prompt. Again, we are going to see a same demo, but with a different machine, which is a OCR data extraction and finding the right data. For demonstration purpose, I'm currently showing using a Postman, sharing a performance task so that you can see the responses generated in real time. Let me bring that screen, go back to Postman and resize the window. Let's resize the window. I'm trying to hit it on this machine as I have started the request. Just observe in background of the screen, the VRAM inside the GPU is getting high. Let me move the window. You can see there was a spike for GPU performance When the query was getting processed, GPU was using at its maximum capacity. As soon as we completed the request, this postman completes the request, the performance step go back to zero. But the VRAM of this GPU is still at high consumption, which defines the model is still loaded inside the GPU. The core concept remains the same, where we access it from the postman, a browser, or from Android app. The communication happens through a REST API calls. This means the same AI power running on high-end Windows machine can consume directly inside the Android app engine, effectively extending local AI capabilities to lightweight or mobile devices. In short, this setup shows how we can scale AI computation from fully on-device model like in our earlier demos to hybrid interfaces where Android device interact with a more powerful edge or local server over secure network. Let me close the postman. Bear with me. Okay. This bridges the gap between the on-device intelligence and edge-based AI computing, giving a flexibility in performance, energy efficiency, and response time. Let's take another quick poll to understand how your perspective is. I'm going to open the poll on your screen, guys. It has been started. I hope it's visible on your screen. The question for this poll is, what's your biggest concern when it comes to adopting AI in medical domain? Good to see your variations in the answers. Poll is live, guys. You can choose any answer among of these. Yep, the poll has been ended. Thank you so much for participating in poll. It clearly it clears that not just one, but all of these factors matters, and in these all are the challenges that our engineering and regulatory team are actively addressing while implementing on-device AI solution to make them faster, compliant, and seamlessly integrated into healthcare workflows. Let's not just talk about the technical benefit, but what are the business value of moving toward on-device or locally hosted AI? First, data privacy and compliances. By keeping all the processing within our organization own infrastructure or devices, we ensure full control over data and patient info. This makes it easier to align with the strict healthcare standards like HIPAA and GDPR. Along with, we have more like cost efficiency, offline capabilities, than customization. In-house team can fine-tune models for specific workloads, devices, or patient needs, creating more relevant and effective solutions. Last but not least, like centralized control on overall system, monitoring and analytics to help us drive a business smooth and secure. Overall, this shift lower cost of ownership while giving a greater control, reliability, and compliances. Roadmap for how we will continue evolving our local AI ecosystem. First, background AI engine service. The goal is to make the AI engine run in the background. This will improve the response time and reduce the responses overhead. Inter-app communication interface. We plan to expose a common interface so multiple apps on the same device can share the AI engine. This enables reuse, consistency, and better responses. Third, local server deployment. For larger setup, we will host the AI on secure local that multiple devices can access via private network. This provides centralized control, easier update, and higher computation capacity without cloud dependencies. Fourth, industry specific model training. Finally, we will work towards training or fine tune models for specific medical domain like radiology, neurology, or respiratory care, to ensure all the AI speaks the same technical language as clinics and delivers context aware insights. In short, this roadmap moves from single device intelligence to connected hospital wide AI ecosystem, private, scalable, and fully under our control. Before we conclude today's session, I would like to take a moment to share a quick overview of the services we provide as a part of our organization core expertise in the medical and healthcare domain. We specialize in on-device AI and edge LLM deployment, end-to-end product development, custom software and firmware development, hardware and mechanical design, software verification and validation, system engineering and risk management, regulatory and quality compliances, QMS documentation, implementation, and training, sustaining engineering, including remediation. In addition to these, we are now advancing into the AI and on device intelligence, focusing on the integrating AI driven analytics and language models directly into the medical devices and hospital infrastructures. This initiative is exactly what today's webinar and demonstration have been about, showing how AI can operate securely with healthcare environments, enhancing clinical insights, patient monitoring, and decision making, all while maintaining full compliance and data privacy. Our mission is to combine regulatory grade engineering with cutting edge AI innovations, enabling a new generation of smart, connected, and intelligent healthcare solutions. Thank you all for joining today's session and for being a part of this journey towards redefining AI and LLMs for healthcare applications. All right, that's it for today. I hope this session gave you a deeper insight into how on device intelligence and large language models are redefining the future of AI in healthcare application, driving smarter, faster, and more effective solutions right at the edge. We would be more than happy to support in your product design, development, prototyping, optimization, or troubleshooting needs. We use the latest AI and embedded technologies to help you innovate faster in healthcare. Please note, a recorded version of this webinar will be available on our website within a week. We will also share a access link with you via email on your registered email ID. Once again, thank you all for your time and patience. Have a wonderful day ahead. Thank you. Bye bye.